80-50, okay. All right, 80-50. Do I hear 81? Do I hear 80-75? Okay, going once, going twice. Sold for 80-50. Yeah. And what's your name? Not sure. Like the chips. Okay, sorry. Okay. Okay, very good. So if you're the winner of any of those auctions, please arrange to pay me today or on Thursday, and we'll proceed. Now, this messing around with risk isn't. I'm not. This is meant to motivate the following graph or the following figures. So Greece has been in the news recently. The reason it's been in the news is because in the past it's issued quite a large amount of debt. I think 140% of GDP is roughly where they're at right now. I think it's 140%. So this is the Greek bank has stopped publishing the prices of their the prices of what their bonds are selling. They stopped on the 27th, which I guess was a week and a half ago. And the maturity, this first column is maturity. So the shortest maturity bond that the Bank of Greece tells us about, they have shorter term debt as well, but the only published data I could find usually has a 3-year maturity with a yield of 35%. So that's greatly in excess of yields that you guys were willing to offer me credit at. Thank you very much. But look what happens as we go over time here. So a 3-year maturity has a yield of 35. A 5-year yield has a yield of 30, and it just keeps on going down until 30 years out. The yield is 14%. Now, 14% sure isn't bad, but it's a lot less than 35%. So this is again a sort of interesting case where the bond market is making some judgment about the risk, probably not of default. Greece can threaten to default, but probably what usually happens with sovereign debt is somebody works something out. Investors take a haircut. So the markets are expecting that there will be for 3-year maturity. Actually, compare this to the U.S. 3-year maturity is 0.38%. So compare. What's the wrong way? So compare this 0.38, which is sort of what you get by investing in a U.S. security with a maturity of 3 years, to the Greek case, where you are demanding 34% more. So the markets are assessing a rough, if there were to default, they're assessing roughly a 1/3 probability of total default over the next 3 years, or a higher probability of some kind of rescheduling that pays investors less than the full face value of their bonds. That gives a yield curve that looks like this. So compare this to the U.S. Yield curve we saw a little bit ago, which you'll recall started off low and went high. Here's the Greek case, which just assigns really high rates. And I think if you actually were able to look at shorter-term maturities, the yield would be even much higher right now. And extremely responsive to news. So, over the weekend, I think Friday, Greece talked about announced they're going to have a referendum on a bailout, and then they changed their minds. Those kinds of news events generate huge changes in yields on short-term maturities as the bond markets try to figure out what the probability of losing money on these investments is. Anyway, so we got a yield curve here. This is called, guess what? This is called an inverted yield curve for sort of obvious reasons. It's a very anomalous sort of shape for a sovereign country to have a yield curve that looks like this. And basically, the bond markets are making a judgment that there's a high probability of Greece defaulting on its short-term debt over the course of the next few years. Yes, Hillary. I think I don't know one off the top of my head. I think it would be an unusual yield curve. You have to have the judgment has to be that there's a lot of sort of short-term risk and not so much long-term risk, and that's sort of unusual. Usually, the long-term risk sort of adds up short-term risk, so this is pretty anomalous. It's not unheard of by any means. U.S. recessions are often preceded by an inverted yield curve, although an inversion of this magnitude is totally crazy. Okay, so that's just a note on the Greek crisis. And with that, it's tempting. Yield. I mean, so a yield of this is your annualized interest rate. So. What you expect to get back here over a 3-year thing is an annualized yield of 35%. So returns are very high, but I mean, so I get a small amount on that, but I wouldn't mortgage my house and purchase Greek securities with it. Okay. All right, so I want to talk now about the relationship between interest rates and present value. So we're going to shift from a world where interest rates depend on the maturity of the issue to a simpler world where interest rates don't change over time. This is mostly for pedagogical reasons. It's going to keep things a lot simpler. I'll make some nods as we go along to handle the case where interest rates vary over time. Okay. So this is kind of an accounting. So we talked about yields as annualized yields. Yields as being an annualized interest rate. That's one way to sort of compare the value of investments that have different interest rates and pay off over different time periods. Here's a more sort of here's another way to do it, which you'll find more often in economic analysis, and which is particularly important. I mean, it's sort of critical when you're trying to think about the value of a resource today versus the value of a resource for tomorrow. And so it's related to the problems we've talked about for extractive industries. I'll come back to that again on Thursday, I guess. It's also completely relevant to the decision you make about making an investment. If you decide to invest in putting, say, solar panels on your roof or something, the trade-off you're going to make is how much does it cost me to make an investment today versus the value of the savings that I receive over time as a consequence of that investment. And so both of those things will involve, and it sort of the whole range of investments you can think about involve calculations of present values. Any of these decisions have an important intertemporal component. Present value comes into it. Okay, so here's how I want to approach thinking about this. The problem is the following. Imagine, I've said it here. Suppose you had a choice between getting, or suppose you were imagining getting $100, but you weren't going to get it today. Instead, it was like one of these bonds at this auction, and you're going to get it. You're going to imagine getting the bond a year from now. And so we just had an auction. You guys were able to come up with some values. $87 was the present value I listed from Brian. I think was a high bidder for that one. But there's an opportunity cost to that $100. You could be investing it in some other instrument that paid off, an interest rate of R, U.S. Treasury or something like that. And so a way to think about this is if you're going to receive $100 a year from now, what is that worth today? So short of having an auction like we just did, that's one way to establish the value. How should you calculate in the absence of a market for this thing? Okay, so here's a trick for thinking about that question. If you think you're going to get a payment of $100 in a year, then and you want to ask yourself, how much is that worth to me today? Then a way to answer that question is to ask, well, gee, how much money would I have to take today and set aside, invest today, so that my total value of my principal and interest 1 year from now was equal to that $100? So it's a calculation that's related to this one. Actually, it's exactly this one for 1 year. If you invest a quantity of money V today, and you're going to get back interest R over the course of 1 year, we want to find the value of V so that receiving an interest rate, well, you know the interest rate. We're going to assume you know the interest rate here. So the value of the principal you invest plus the interest you get back gives you $100 1 year from now. So you can see there's some very simple algebra here, which I just reproduced on the board there. So this is just equal to V. This is the principal. This is the interest. I'm sorry, V plus VR is the interest on the principal, and that has equal $100. So of course this implies that V has to be equal to this $100 divided by 1 plus R. Okay, so that's the calculation. And this V is what we'd say is the present value of $100 1 year from now, if you face interest rates are. So notice it's a function of interest rates. The higher the interest rate is, the higher the opportunity cost of your $100. So if interest rates were 100%, so we have 1 plus 1 in the denominator, the present value would only be $50, because the opportunity cost of your $50 was very high. So having a high R here tells you something about the opportunity cost of your investment. All right, so this is one way to compute the present value. All right, so that's what we do for 1 year. Let's think about extending the logic here and doing this over different quantities of years. So we started with the calculation here. V times 1 plus R equal to $100 gave us the present value, which is 100 divided by 1 plus R. For 2 years, what happens? The math is up on the board there, but let me talk you through it. In 2 years, what happens is you start off with an initial investment today of V. Let's make this not a weekly interest rate. Sorry, I should erase that. This is annual interest rate now. So it's V times, you get the principal plus interest back on that. But then, if you're going to get $100 2 years from now, you can reinvest the principal and interest so that the total is V times 1 plus R times 1 plus R, and that has to be equal to $100. Now, in this case, this implies that V is equal to this $100 divided by 1 plus R squared. So this is for a maturity, make this equal to 2. Is that clear? You can see the calculation up there. Is the nature of the calculation clear? If I invest $1 today, I get back $1 plus interest tomorrow, next year. I can reinvest that $1 plus interest next year and get interest on it. I can go to third year and so on. And so that tells me, if the question is, I want to think about the value of $100 10 years from now, then the present value of V is going to be equal to $100 divided by the interest I could have earned on that thing for all of the T years that passed before I get my $100 back. So this is how to compute the present value on a simple bond when interest rates don't vary over time. Okay, now there's some things we want to do differently. There's a simplification here that we've already seen. Let's look at this yield curve here, or the yield curve on U.S. Treasuries. You can sort of see, well, interest rates aren't really constant. If they were, these lines would be flat. Any thoughts about how we could accommodate having interest rates that change over time here? Yeah, let's go. Yeah, that's good. So this is like the interest rate in year 1. So we put a 1 there. Interest rate in year 2, we do that. So here we wouldn't have 1 plus R squared. Instead, we have 1 plus R1 times 1 plus R2. In the general case, we have V equal to $100 divided by the product, T equal 1 to cap T of 1 plus RT, something like that. So that's how you handle the general case, where interest rates were varied over time. Notice that we're still assuming that they're known. You need to know what the future interest rates are to do this calculation. So there's still not really risk embedded in this calculation. Okay. All right, so we've done this calculation. I'm going to do one more thing before I let you go today. So we've answered the question, if you get $100 T years from now, what's its value today? We know how to answer that question now. Actually, is that clear to everyone? If you know what interest rates are, and you know you're going to get $100 T years from now, here's how you can compute the value. Okay, now how then would you figure the present value if we were going to get $100 every year? So this is called a perpetuity. A perpetuity is a kind of asset that gives you a fixed payment every year for sure. So forever, by the way. So a perpetuity is, an example of a perpetuity would be an asset that gave you $100 every year forever. Give it to your heirs upon your demise and so on. Okay, so you can buy and sell perpetuities. How would you compute the present value of a perpetuity? Luke? Okay, so let's assume that, so this is for the purpose of this exercise, we're going to assume that we know the interest rate and it's fixed. But let's start with that. Yes? Yeah, it's extremely simple. If you know what the value of $100 is, 1 year from now, and you know what the value is 2 years from now, and 3 years from now, and so on, just add them all up. Okay, well, so that's not so hard to do. The present value of a perpetuity, then, we're going to use this general form. We'll have V here. We're going to add up from little t equals 0, so that's like now, to cap t. Actually, let's imagine we just do it t years right now. So then we'll have 1 over 1 plus r, this whole thing raised to the t, all times $100. And notice in this case, $100 doesn't change over time, so you can actually just factor this out. And for the case of a perpetuity, we have t equal to infinity. Does anybody know how to compute the value of that infinite sum? There's a trick that this is a very useful trick in these kinds of exercises. Let me tell you what it is. If you have an infinite sum, t equals 0 to infinity, of a number alpha raised to the t, where we need to assume that the absolute value of alpha is less than 1, strictly less than 1. If it's equal to 1, what's the value of the sum? It's infinity, so that's easy to compute, but not very interesting. So if it's less than 1, though, it turns out to have a finite value, which is equal to 1 over 1 minus alpha. So that's the value of that infinite sum. We can do the same trick here, because this 1 over 1 plus r is just like this alpha. So the value of perpetuity, with t equal infinity, we get v equal to $100 times 1 over 1 minus 1 over 1 plus r. I think it's okay. So this is because 1 over 1 plus r is this like value of alpha. And then we can simplify this thing, though. So we have $100 times, and I always have to get this right, times 1 plus r all over r. Okay, so this is the value of a perpetuity that pays out $100 every year forever. So a calculation like this is, it's useful if you want to price perpetuities. It's also useful as at least a rough sort of rule of thumb. If you're trying to make an investment, like an investment in improved insulation in your house, where you think you're going to have energy savings of roughly $100 per year, then the calculation, the value of that investment to you today, that calculation will resemble this one. Okay, let's stop there. I will pick this up on Thursday. Thank you.